Oh, really did change size, didn't it? Okay, so
Speed distortion.
what's the motion here? Let's ignore air resistance. What's the motion? It's falling, so
It's accelerating.
it's accelerating. It's getting faster and faster, isn't it? So what's happening to its kinetic energy?
It's getting less and less. No,
No,
it's
it's
getting more and
increasing.
more.
More. Because it's getting more massive? No, because it's getting more velocitive. It's going faster and faster and faster. Okay? What's happening to its potential energy as it falls?
Going down.
It's going down, right? So let's say we have 1,000 joules of potential energy up here, and our kinetic energy, I should be using different symbols, but whatever, you're good, is 0. Because, well, how could kinetic energy be 0? That's if the object is,
It has a zero velocity.
yeah, it's not moving. Not moving. Bang, we let it go. Halfway down, well, it's got some potential energy. If we're at half the height, what's the potential energy? Halfway down. It's half the amount, so that's going to be 500 joules. Where'd it go? Into the kinetic energy. If you know the mass of this thing, you can find out how fast it was going. And then if you go back, remember when we did those tables for free falling objects? Or remember when we did the no VF or the no VI or the no acceleration, no time or no displacement things? You can use that way to figure out how fast something is falling, but you can also use this, conservation of energy. Because when we get to the bottom here, what's our potential energy down here?
Zero.
Yeah, we're like the width of a human hair from hitting the ground. We got a potential energy effectively of 0, and a kinetic energy of how much? 1,000 joules. This is what we call the first law of thermodynamics.
First law of thermodynamics, we don't talk about thermodynamics.
Yep. First law of thermodynamics is energy is conserved, and I know you've heard this before. Yes? I'm sure Ms. Hageman has said that to you, and I suspect Mr. Kelly did too, and I bet Mr. Mills did, and I bet all those other sciencey people in your history did. Okay? But what did we ignore in this example? We ignored air. Okay. So the second law of thermodynamics it doesn't look like it. Right? It's that simple. Energy is conserved. Well, it doesn't look like it. It's just like objects in motion, they stay in motion. You're like, it doesn't look like it. Anytime I get something in motion, it stops. Doesn't it? Right? You give your skateboard a push on the road, it stops. Right? You're rolling along on your bike, you just stop. You're like, damn, I got a pedal. I'm supposed to keep going. Right? So energy is conserved. I guarantee you it is conserved. It's just that it doesn't tend to stay in the same form. Because where's the handwriting? P-E-C-A-U-S-E. Because of friction, air resistance, etc., etc. This etc. part is pretty big, and we will address what etc. is. But in the end, the first law of thermodynamics is like, yes, we do 1,000 joules of work up to here, we drop it, it's got half of that halfway down, the other half is in the kinetic energy, and when we get to the bottom, all 1,000 joules are still present in the object. Second law of thermodynamics is like, actually, not really, kind of, depends on the object, depends on the air resistance, depending on how far you dropped it, right? It's just like our falling objects thing where it's like, all right, do they speed up at the acceleration due to gravity? Stapler? Probably for a little while. Piece of paper? Nope. Shot put? Yeah. Shot put's pretty accurate, actually. Yeah, for a while. But if you drop a shot put from an airplane, it's gonna reach its terminal velocity. It'll reach a point where it's not falling any faster. So it's doing a lot of work on the stuff. So it doesn't even work for that in really large examples.